Right, we continue our morning session with one of our first distinguished lecture speakers in the past, Professor Dennis Gaitsgory, and he is going to share his thoughts on Langlands related problem with us today. Thank you, Dennis.
Thank you. Yeah, so should I start?
Yep.
All right. So I'm going to describe recent progress on the geometric Langlands conjecture. So all of this is a joint project with several people. So it's Arinkin, Beraldo, Chen, Faergeman, it's myself, Kevin Lin, Sam Raskin, and Nick Rozenblyum.
Can you unmute yourself, please? Thank you.
Oh, I was on mute the entire time?
Yeah.
Oh, sorry. So I listed the co-authors of this project, and so it's a recent progress in the proof of the geometric Langlands conjecture. All right, and first I'll describe the two contexts in which it was formulated, namely the Rham and Betti. So here is the Rham context. So in this case, we work over an algebraically closed field K of characteristic 0. And so there is the automorphic side and the spectral side of geometric Langlands. The automorphic side looks as follows. So we fix X and G, both are, so it's a curve, a smooth complete curve. And G is a reductive group over K. And we form the moduli stack bun G of X. So it's the moduli stack of principal G bundles on X. And our object of study is the category, so in this case, the derived category of D modules on this stack, and I denote it by D mod bun G. And so this is, because we're in the context of D modules, this is what we call a DG category or stable infinity category over K, tensored over the same K, which was our ground field. So this is the automorphic side. So now let me formulate the spectral side. So in this case, we consider so G check with the Langlands dual group, and we consider the stack log sys G check. It's the stack of the Rham local systems with respect to the Langlands dual group. Let me, so because it'll be important very shortly, let me say explicitly what the stack is. So it's also an algebraic stack over K, and let me say what its points are. So if I want to map an affine scheme to it, from spec R to log sys G check. So this is by definition the category of, so it's a groupoid of symmetric monoidal functors from the category of algebraic representations of this group in question, in which case it's the Langlands dual, to the category of, so I can write it like this. I can write it D modules on the curve, tensor R modules. But all it says, in fact, this is just the category of D modules that are also equipped with the structure of R modules. So these are, so D module equipped with an action of R. So this is kind of the definition of log G as a functor. And so what we consider in this category, we consider, well, on the first glance, you want to consider the category of quasi-coherent sheaves. This is not quite right. So one has to make a modification and instead consider what are called incoherent sheaves with nilpotent single support. However, this will get a little bit too technical, and for that reason, for this talk, let's ignore the difference. Let's pretend that these are just quasi-coherent sheaves. In any case, the difference occurs at the cohomological negative infinity. So, and the geometric Langlands conjecture predicts that there exists an equivalent between these two. So this is the geometric Langlands conjecture in the de Rham context. So now I'll describe a parallel world where, in which geometric Langlands conjecture can be formulated. But this is the Betti world. So Betti context. Oh, by the way, let me just stop for a second and see if people have questions.
Yeah. So is what is quasi-coherent sheaves kind of modules for everything R module?
Sorry, I didn't hear so well. Can you please say again?
Such a quasi-coherent sheaf, does it correspond to some functor from, let's say, R to R module?
No. Ah, well, yes. Yes. So a quasi-coherent sheaf on a stack, what it is, it's a compatible, so what is it? It's for any spec R point of log cis, it attaches an R module, and in a way that's compatible with pullbacks. So you have R1 mapping to R2, then what you get for spec R1 mapping to a spec R2 to what you have on spec R1 is the pullback of what you had on spec R2. So that's exactly that. With this small correction that, I mean, everything is derived. So when you're talking about quasi-coherent sheaves or R modules, I mean, not just objects of the abelian category, I mean, objects of the corresponding derived category. Does that answer the question?
Okay.
All right. Any more questions at this point? All right, so let me proceed with the Betti context. So on the surface, it looks the same. However, so here is an interesting dichotomy. So our algebraic geometry will take place over the field of complex numbers, but our field of coefficients, namely the field over which our differential graded categories are tensored over, is an arbitrary algebraically closed field of characteristic 0. So algebraic geometry is over C, and coefficients arbitrary algebraically closed field of characteristic 0. Field, let me call it E. So now, what is the automorphic side? What is the spectral side? So I'll start, in this case, first by formulating the spectral side. So the spectral side is also the stack of local systems, G-check, but in the Betti world. So let me put here Betti, and let me put here de Rham for this discussion to distinguish them. So, and the remarkable feature is that this stack is an algebraic stack over E, not over complex numbers. And on the spectral side, we'll consider, well, quasi-coherent sheaves in the same sense as before, and with a correction to intercoherent sheaves with nilpotent single supports, what they are. But so, and there will be also the automorphic side, but let me first specify what that stack is. And so it's defined as follows. So also we specify our points. And again, it's a stack over E. So R is now an E algebra. So these are symmetric monoidal functors. And here, G check is perceived as an algebraic group also over the field of coefficients, over E. So there's a symmetric monoidal functors as follows. So I write here sheaves, by which I mean Betti sheaves. Tensor R mod, which again you can think of as just Betti sheaves of R modules, or Betti sheaves of E vector spaces with an action of R. Okay, so this is the spectral side. Now, what's the geometric side? You consider Bun-G, but remember, the curve was over complex numbers. G was a complex numbers. Bun-G is a stack over complex numbers. And naively, you would consider all Betti sheaves on it, but with E coefficients. But that turns out to be very wrong. And so this category is huge, and you will see that it's too big when you consider the case when G is a torus. And what you have to do is you have to consider the condition of on the singularities of the sheaves. So I put the condition nilp, it's condition nilpotent single support, not to be confused with nilpotence on the spectral side, which I brushed aside. So let me say a few words what it is. So in general, if you have a space, and if you consider some subset of its cotangent, so let's say Y is a manifold, then you can, if you have a sheaf on Y, by the theory of Kashewara and Shapira, you can attach to it its singular support, which is a subset in the cotangent bundle. And you will say that, so definition, so if you fix the subset, this is the full subcategory consisting of all sheaves, all objects such that their singular support is contained in N. And in the case of the cotangent bundle, sorry, of Bun-G, so T star of Bun-G is known as to be the space of Higgs bundles. So it is equipped with canonical map to the Hitchin base. And so what I called nilp, so let me call this map R, and what I called nilp is the nilpotent cone. It's the pre-image of zero. So in the case of GLM, so let me write explicitly, Bun GLN is the space of pairs. So MA, where M is a rank N vector bundle, on the curve, and A is an endomorphism with values in the canonical line bundle. And so nilp is exactly the set of those MA where A is nilpotent, i.e. if you iterate it n times, you will get zero. And so the geometric Langlands conjecture in the Betti setting says that there exists an equivalence like so. And so the kind of most of my talk will be devoted to the de Rham case, but I'll spend now a few minutes explaining how you can deduce the Betti case from the de Rham case. But let me again pause to see if there are questions. Questions?
Yeah.
Okay, but do you have any extension to the general situation where you don't put this importance of condition?
Sorry, for some reason I couldn't hear very well. So I do have what?
Can you generalize the right hand side so that it matches the left hand side?
No, so no one knows that, and I don't expect to be there to be a more general conjecture where on the left hand side I have all sheaves, on the right and so yeah, I don't so this is not expected. Somehow, if you consider all Betti sheaves, there are too many of them, and so you'll now see something, a related phenomenon in what I call the restricted context. All right, so now what I'll describe is what I call the restricted Langlands conjecture in both contexts. So let's briefly return to the de Rham case. And so I'll copy the statement of the Langlands conjecture. So I have D modules on Bungie equivalent supposedly to quasi-coherent sheaves on log-cis G-check de Rham. So, but in here, one can consider D modules with nilpotent singular support. The theory of singular support makes sense for topological sheaves, but also for D modules. And so this subset nilp is Lagrangian, so therefore all these D modules are automatically holonomic. And you can ask, what does this category correspond to on the right-hand side? And there is an answer. So it would be quasi-coherent sheaves, again with the same correction that it's of homological nature, on another geometric object that are called de Rham restricted. And let me explain what that is. So this is a substack inside the de Rham version of de Rham version of the stack of local systems. So, and what you have to do, so you have to modify the definition as follows. So in the definition of log-cis de Rham, I took the category of D modules on X. And if I want restricted, I can consider the subcategory of ind local systems. So let me say that. So in the definition of log-cis de Rham, replace D mod on X by D modules that can be, well, the many equivalent definitions. You can say ind holonomic. And so, and you can show that if the original geometric Langlands conjecture holds, then it implies that these categories are equivalent. But more surprisingly, there's an implication in the opposite direction. So, GLC de Rham version is actually equivalent to GLC de Rham restricted version. And something similar also occurs in the Betti version, so let me write now Betti. So here we originally considered sheaves with nilpotent singular support, but these were arbitrary sheaves, so with infinite dimensional fibers. But here one can consider a subcategory of sheaves which are inconstructible. So the original geometric Langlands conjecture said that this was equivalent to quasi-co Loxis Betti as is, and there is a restricted version that says that this is equivalent to quasi-co Loxis Gchek Betti restricted. Where Betti restricted, it's replace in the definition of Loxis Betti, replace the category of Betti sheaves on the curve by inconstructible ones. And and again, we have the same story. So the original GLC, the Betti world, implies the restricted version, but also we have the opposite implication. But now, so once we have that, you can show by, so Riemann-Hilbert implies that GLC in the de Rham restricted world is equivalent to GLC Betti restricted version. So therefore, if you prove the full de Rham GLC, from it you deduce the restricted de Rham GLC, from that you deduce the Betti restricted GLC, from there you deduce the full Betti. So that's how, so that's the mechanism by which the de Rham version of geometric Langlands conjecture implies the Betti version of the geometric Langlands conjecture. And from now on, I'll focus on, well, I'll explain the kind of main ideas that go into the proof of the de Rham version of GLC. Are there any questions at this point? Any questions? All right, so here is the main ingredient in the proof, and it kind of parallel to many other instances in which Langlands has been proved, and it's spectral decomposition. So before we try to prove that these two categories are equivalent, we'll try to make the spectral side act on the automorphic side. So, and it's called spectral action. There is a canonically defined action of quasi-co Loxis Gchek de Rham on the category of D modules on Bun-G. So let me say a few words how that proceeds. So this construction involves one of the most well-known ingredients in the Langlands theory, namely geometric satake. So what is known is that if you fix a point on the curve, and if you fix a representation of Langlands dual group to it, you will be able to attach an endofunctor. It's called a Hecke functor HXV is an endofunctor of the category of D modules on Bun-G. So you can still keep the point x fixed and vary v, and what you'll see is you'll obtain for every point x on the curve, you'll obtain a monoidal action of rep G check acts on the category D modules on Bun-G. So now you can start varying the point x, and moreover, you can have these Hecke functors act at several points, and then you can let these points move along the curve and collide. And so all this thing together forms a category that has a name. It's called rep G check Rham. Rham is the Rham space, so it's the space of all finite non-empty collections of points on the curve. So it's a particular symmetric monoidal category that examples of objects in which are as follows. So if you fix points x1, xn on the curve, and if you fix representations v1, vn of the Langlands dual group, to it you will be able to attach a representation, an object, okay, v1, x1, tensor, vn, xn, and this object of the category rep G check on the Rham space. But you can also let the points x move, and along the, so they'll move along powers of the curve, and along these powers you can put d modules on this power, on the corresponding power of the curve, and you can also let them collide, and that will correspond to tensoring up these appearing representations. And all this thing together, so these Hecke functors give rise to an action of rep G check Rham as a monoidal category on D of Bun-G. So the action of this symmetric monoidal category is what encapsulates the totality of the Hecke actions. So this is observation number one. Observation number two is the following, that so this category is related to the category of quasi-coherent sheaves on the stack of the Rham local systems. So namely, it's related by what we call the localization functor. So namely, so let me say what this localization functor, what it does on an object that I wrote above. So the nxn. So if you fix a point on the curve, you have the evaluation map, that we call it m sub x, from the stack of local systems to the classifying spec, BG check. So you just restrict your local system to this point, and note that you can think of representations of the group as just quasi-coherent sheaves on the classifying stack. So the formula for this object is the tensor product over insertions of evaluations pulled back of the corresponding representations. So kind of the dilemma is that this localization functor is a Verdier quotient, which means that which means that it admits, so it tautologically admits a right adjoint. This right adjoint is fully faithful. So what's the upshot? Upshot is that in such situation, if you rep G check Rham acts on some category, in this case D mod and Bun-G, there is at most one way to factor this action through this localization quotient, and so it's quite a non-trivial theorem. So it's Drinfeld and myself that says that so the action of Reb-G-check run on dmod Bungie factors through an action of quasi-co loxis G-check. All right, so this is the story of the spectral action. And again, let me pause for questions. All right, so now let me proceed with the construction of the functor in one direction. So the construction of the functor in one sorry, am I audible? Can people hear me? Yep, okay. All right. So the construction of the functor in one direction is motivated by number theory, which number theory says that Langlands, so number theory, Langlands correspondence is normalized by the Whittaker model. So, and the same thing will happen here. We'll construct the functor in one direction. I'll call it LG, the Langlands functor. And it will be uniquely characterized by the following property, that it makes the following diagram commute, where the right slanted arrow is the functor of global sections, and the left slanted arrow is the functor of Whittaker coefficient. So let me call it a vacuum with Whittaker coefficient. So let me say a few words of what it is. I'll give an example. Well, explain it what it is for SL2, and generalization of an arbitrary reductive group is pretty straightforward. So, so we consider the following step. It's called the twisted version of this of Bun N. N is the maximally idempotent group, and so I call it rho of omega. It's this twisted version. I'll explain what it is in a second. Of Bun N. So here is what it is. So what is Bun N? Bun N is you take Bun B, modular stack of bundles with respect to the Borel, cross over Bun T with the trivial bundle, where one is the trivial bundle. And the twisted version is the following. It's Bun B, Bun T, and instead of taking the trivial bundle, you're taking the bundle induced by the sum of positive roots to rho from the line bundle, which is a chosen square root of the canonical bundle of the curve. So the theory of Langlands correspondence depends on the choice of a square root of the canonical bundle. So, and I'll explain in a second how it looks like for SL2, but in general, so we'll have a forgetful map down to Bungie, and the specifics of our choice of this T bundle will be that there will be also a canonical map to the additive group GA. So let me explain how it looks like for SL2. So for SL2, classifies short exact sequences that look as follows. So this is our chosen square root of the canonical bundle, and here it's negative. So this this map P just remembers the middle term M, and the map chi assigns to this extension its class. So note that x1 from omega 1/2 minus 1/2 to omega 1/2 is the same as h1 of the curve with coefficients in omega, and by seriality, this is the same as our ground field. So remembering the class of the extension is a map to GA. And so this kind of picture exists for an arbitrary reductive group. So, and the functor of vacuum Whittaker coefficient is defined as follows. Is the composition of the following functors. You first pull back with respect to this projection P, and you push forward with respect to this map chi, you land on GA, and so you obtain a D model in J, and then you apply the Fourier-Mukai transform. So, and then you take fiber at 1. Or you can also rewrite it as follows. You can say that it's cohomology chains on the stack bun, this twisted form of bun N of the pullback of the D module on bun G, tensored with the pullback of the exponential D module by means of chi. So you tensor and then integrate. So I'll now construct a functor in one direction that makes this diagram commute. So, well, and this will be something easy to do. So namely, the functor of vacuum coefficient is co-represented by an object called the vacuum Poincare sheaf, is home from and this vacuum Poincare sheaf is just below a shriek, chi upper star of the exponential. And we'll first define a functor which is left adjoint to this Langlands functor. LGL. So recall that we said that this category of D modulus bun G is already a module category for this category quasi-co. And so we want to define a functor in one direction, and moreover, we want this functor to be a functor of module categories. Such a functor is determined by a choice of an object on the target, and that object we set to be the Poincare sheaf. So in other words, there exists a unique functor which is linear with respect to the action of quasi-co, and that makes this diagram commute, where this right arrow sends the generator to the structure sheaf, and the right arrow sends it to this Poincare object. And by passing to right adjoints, you obtain the diagram that I wrote. And so the more precise version of the conjecture, so now theorem, is that this functor LG is an equivalence. All right, so, and again, let me pause to see if there are questions. All right, so now let me, so now the proof begins, and let me just indicate the main ideas. So the first step, as one usually does in the theory of automorphic functions, one studies the interaction of the group G with its Levy subgroups. So if you have a parabolic P inside G with Levy quotient M, then you have then the corresponding parabolic in the Langlands dual. You can consider the diagrams so you can consider these diagrams on both the spectral and the automorphic sides, and so they define functors between the corresponding categories. Let me call this PQ. We call it P spec, Q spec. We define the Eisenstein functor to be Q upper star, P lower, Q upper star, P lower shriek, and it has the right adjoint, which is constant term functor, which is P upper shriek, Q lower star. And similarly, on the other side, there is a spectral Eisenstein functor. It's P lower star, Q up spec, Q spec upper star. So note in this case, P spec is proper. So this functor P spec lower star is naturally left adjoint, and constant term spec is P spec upper shriek, Q spec lower star. So the first theorem one proves that the Langlands functor is compatible with all of these. That so you have D modules on band M, you have Q co log cis M check. There is a Langlands functor for M, and there is the corresponding diagram for G. And so here are this Eisenstein constant term functors. And so this diagram commutes both ways. So that's kind of the first major theorem one proves. So implying the Eisenstein constant term compatibility of the Langlands functor. So let's denote by D mod band G sub i's, so the full subcategory. So generated by the essential images of the functors I shriek for proper parabolics. P side G. And let's also denote by quasi-co log cis G check red the full subcategory consisting of objects set theoretically supported on the locus consisting of reducible local systems. So that's the locus. So the second theorem one proves is the following. So here one argues by induction a semi-simple rank. So assuming GLC for proper levies, that so that the functor LG defines an equivalence from this subcategory, this Eisenstein generated subcategory, to this subcategory on the spectral side. So that's the second main result in this theory. And so that reduces the proof of the geometric Langlands conjecture to kind of the most interesting case, namely the cuspidal versus cuspidal case on the automorphic side and irreducible locus of local systems on the spectral side. So let me again pause for questions.
Going back to the extension that you have of the square root of the canonical.
Say one more time, going back to?
The extension that you had of the square root of the canonical by the inverse.
Yeah.
There is something for any group. So I guess it's a reduction to parabolic. You have to choose all.
So So if you look at the, so I wrote the so here I'm circling in red this definition, and if you look at what it is, it will project, the stack will project to a product of copies exactly of this stack, one copy for every vertex of the Arinkin diagram. And so in this way, the stack will have naturally defined map to a product of copies of GA, as many copies as there are vertices of the Arinkin diagram, and then you take their sum to obtain a single map to GA. Does that answer the question?
Yes, thank you.
All right. Okay, so assuming this theorem, what we have to do is the following. So let's denote by d mod Bun-G cusp the right orthogonal full subcategory inside d mod Bun-G. And so you can also similarly consider the category quasi-Coherent sheaves on the stack of irreducible local systems, which is naturally full subcategory inside all log-cis by means of just direct image with respect to the corresponding open embedding. So therefore, so remains to prove that LG induces an equivalence d mod Bun-G cusp to quasi-co log-cis G-check irreducible. So let me call this functor LG cusp. And so moreover, this functor LG cusp is linear with respect to quasi-co. So there is a functor that is left adjoint. So now let me indicate the main steps that went into this. So the main thing was the theorem that was proved by Faergeman and Raskin 2 years ago. So it says that this functor LG cusp is conservative. So it doesn't kill anything. So this theorem, in some sense, kind of unveils the main mystery of Langlands correspondence. So we kind of, until this moment, we didn't know why aren't there too many cusp forms in the geometric setting. But it turns out that there are none. So like they're all completely caught by Langlands parameters. So once you have this, what you have to consider is the following. Consider this monad. So this functor preceded by its left adjoint, and so it's an endofunctor of quasi-co log-cis G-check red, and moreover it's a linear endofunctor. So therefore it's given by tensor product by some object. So it's given by tensor product with some AG, and it's not only an endofunctor, it's a monad. So AG is an algebra, associative algebra object inside the category of quasi-Coherent sheaves. And so what we have to show is that the unit map for it is an isomorphism. So we've reduced the question of Langlands correspondence to one map of sheaves associative algebras being an isomorphism. So now one performs a few more steps. So there's another theorem, it's called ambidexterity. It says that this left adjoint in the cuspidal context is actually isomorphic to the right adjoint. And so this theorem relies on a whole new layer of theory that has to do with localization at the critical level. So there's definitely not enough time to talk about that. And so what this implies is that this AG is a perfect complex. And so one can go a few more steps. So one can show that it's not only a perfect complex, it's in itself dual. So G is self-dual. So then there are another set of considerations that, again, has to do with localization. It has to do that it says that it lives in cohomological degrees that are non-positive. And because of self-duality, it implies that it lives in cohomological degree 0. So it's a classical vector bundle. And then there is yet another layer of considerations that says that this vector bundle is actually equipped with a flat connection. And so this is where we were about 2 years ago. And then we invented a bunch of tricks to show that the geometry of the stack of local systems is so constrained that just these properties formally imply that basically there's no wiggling room, that this AG must be the structure sheaf. So what happens is that in genus 2 higher, this stack of local systems, of irreducible local system, is simply connected. So this AG would be, in any case, the direct sum of copies of the structure sheaf. And then one can rule out that this direct sum, in fact, is just a single copy of the structure sheaf. So that's basically how the proof proceeds. So if you wish, it's all theoretical considerations up until this point, and then there's a bunch of tricks that shows that after this situation is so constrained that this AG must be the structure sheaf. All right, so that's basically what I wanted to say.